like that. And suppose we took our light detector and we made a measurement 1 meter away from it in every direction around that light source. We'd end up with a sphere with a radius of 1 meter, and all the light from our light source would have to pass through that sphere. And if I then take and measure the same thing again, but now at a radius of 2 meters away, again, every single photon of light that originated at our point source would have to pass through the surface of that sphere. But now what has happened to the surface area of our sphere?
It's double increased.
It has increased. And actually it goes up exponentially, because the surface area of the square, or of the surface, is going up in proportion to the square of the distance. So the surface area goes up exponentially, and if you've got the same amount of light passing through an area that has increased exponentially, well then the intensity, the amount of light per unit of area, drops off inversely, exponentially. And so we get an inverse exponential relationship with light. One of the things that came up the other day, we were talking about how Romer and some of those other guys tried to measure the speed of light. And I said one of the ideas that had been tried, somebody took a lantern on top of a mountain, and somebody else had a lantern on a mountain 10 miles away. And the idea was that one guy would show his lantern. When that guy over there saw it, he would show his. When this guy saw that one, he would stop timing, and he would know that the light had to travel to there and back. And I made the comment that I don't know what kind of lanterns they were using, that you could see them from 10 miles away. And Skylar and I kind of got into the discussion a little bit, would you be able to see it at all? And said, well, if you have no ambient light around, you'd be able to see it just fine. Do you still think that would be true? If there's no ambient light around, would you be able to see that lantern 10 miles away?
It depends on the intensity of the light and on the sensitivity of your eyes.
Yeah, because can you guys see that as you're increasing the distance, even though your lantern is a nice bright lantern, as you get farther and farther away, the number of photons emitting from that lantern that actually hit your eye end up being fewer and fewer, and they drop off exponentially as you increase the distance. And so it's not uncommon to have like a regular flashlight, like one that's powered with a couple AA batteries, and if you shine it at somebody from maybe 100 yards away, in pretty much the dark, you can't see it very well. And why can't you see it? Sometimes people say, well, you can't see it because the light doesn't make it that far. Is that true?
Hitting your eye, back of your eyes.
Yeah, the light makes it there. There are photons hitting your eye from that flashlight. It's just that the number of them hitting on your retina is so few that you reach the point where you reach the lower limit of resolution of your retina. So if we go out and you look at the night sky, sometimes you can see stars that you can't see other times. But if you go out and you look with a pair of binoculars, you can see gobs and gobs more stars than you can with just your plain eyes. Why is that?
Because the resolution power goes up, the resolving power.
This one turns out it's not so much a deal about the resolving power, but you're on the right track. It's about the area.
Oh, the amount of light that can be collected.
Yeah. If you just look up at the sky, the amount of area that you have available to collect light is the size of the pupil of your eye. Okay? Not a very big opening. But if you're using binoculars, well, that opening is quite a bit larger. You're collecting light over this whole area and focusing it down, and so as a result, you're increasing the intensity of light per square meter. You're making that intensity per area unit much, much higher than it was before. So with astronomical telescopes, usually magnification is not really a big deal with astronomical telescopes. If you go out and get a really good, expensive telescope, they're not going to be bragging in the catalogs that this thing magnifies 400 times or this thing magnifies 1,000 times. What do they brag about?
The collecting area.
Yeah, how big around it is, the surface area. So the bigger the surface area, the more light that you could collect and focus to a point and make things detectable that you couldn't see otherwise.
That was the main
because
thing.
of that inverse squared relationship. Go ahead, Scott.
That was the main thing driving the whole Hubble thing, was having that much light collecting area out there in the space. I mean, also, I don't know how much we want to get into this, but if you have the same amount of area, but you point it at the same space longer, you can collect more, and then you're physically collecting more light, and you can add that together to make.
Yeah, you're exactly right. Like aperture time on a camera, the longer you leave the aperture open, the more light that will come in and end up landing on the screen, and so the better able you are to detect whatever it was that you're trying to look at. And you're right, with the Hubble Space Telescope, why'd they have to send the thing out in outer space? Why couldn't they just make it that big and put it on a mountaintop here on Earth?
Because of the, atmosphere makes a big difference on
That's
what,
an issue.
on what you can see, just with the types of lights that will pass through and the types that won't, but also all the light coming up from the cities and stuff.
An issue also, but an even bigger one was just the weight of the mirror itself. The thing was so big and so heavy, if you take it up and prop it, and prop it at an angle and, and point it somewhere, gravity over time is going to start to warp it and change the shape of your mirror a little bit. And as your mirror changes shape, then it doesn't reflect the light to the correct location. And so one of the reasons that the Hubble Space Telescope was such an attractive idea was that you could put it out so it would be in free fall all the time, and you wouldn't end up with that warping that occurs on a big heavy piece of glass over a long time just sitting in gravitational fields. So your lab reports on this one are right here on this stack. They are called Relatively Bright. Send one person from each group up, grab a data sheet for everybody in your group, and you can finish doing those lab reports as homework. We might be here tomorrow.
Oh, I don't know.
Oh, yeah, no.
Oh, so much. Oh, that's Thursday. There's so much contrary to the other one.
Oh, and by the way, I'm glad Austin reminded me that. If I didn't mention it, retake for the last test is still scheduled to be on Thursday. Even if we have snow interrupting us between now and Thursday, if you want to come in and go over your old tests, there's a little bit of, the snow will kind of mess that up. I will not be here before school tomorrow. Mr. Ponder and I both have some training on the computer that we have to do. On Wednesdays before school, I won't be around. I'll be around after school both days, Tuesday and Wednesday, and today. So if you want to go through over your test, those are kind of the time frames that we've got available. But we're still planning on trying to get the retake done on Thursday, even if we get interrupted by snow. Okay? Because we're getting so far away from that test, I'm afraid that if we get snowed on again Tuesday and Wednesday and then pushed back to next week, that we're just getting pretty far away from that test. So we're going to try and do that on Thursday no matter what. Yes, Andy. Yes, you may.
I heard 2 all over 12.
All right. So, next thing then, I've got a couple things that I would like to show to you that are kind of interesting relating to this idea of what exactly light is. So, the discussion that we just had there, did that shine any light on the nature of light? Is it more particles or more waves, or does that not really help us out any?
Well, I mean, in this scenario, it's acting as more of a wave, I think.
Can you tell me why you think so? Because I would tend to think it doesn't help any.
Well, see, it doesn't really help any, but it doesn't hurt either. It's traveling as a wave, though you're measuring the end of the wave wherever it hits your light sensor.
Okay. If our point source up there, say, was a spray paint can, and it was emitting in 360 degrees instead of just out in the cone in front of it, it would follow that same basic pattern as a light source would, right?
It wouldn't bounce
If you
off.
measured the intensity one distance away and then doubled it, all that paint still ends up spraying the inside of that sphere, so you still end up with the same number of particles, just spread out over a bigger area. Well, if instead of spraying out particles, if you're spraying out waves, same kind of idea happens. So the idea that it's an inverse square is a useful piece of information that will help us figure out some things about what light is doing. But in answering the question of whether it's a particle or whether it's a wave, it doesn't really help too much because either one would show an inverse squared relationship. Skyler?
Except if we talk about the bouncing thing, with not so much with this exact thing, but what you said, like with a light, a flashlight.
Mhm.
Because if it's shooting it out in particles, and we think of it as like paint spraying, if it's particles, it'll stick to the glass, and if it's waves, maybe it bounce off.
True. Although particles bounce also. I mean, if the particles are hard like marbles, they would hit and bounce off. So they don't have to be sticky particles, but I understand what you're saying. All right, so come back over here, and I'd like you to make an observation of this. Okay. If on a day when we have nice bright sunshine coming in through the window, I just set this in the sun to show it, but we don't have much sunshine today, so I'm going to replicate the sun with my light source here. And so, take a look at that thing. If you want to get close and look at it, you can. That's fine. I'm going to turn the light on and shine on it for a minute. These lights won't hurt anything.
One side's black, one side is
Each of the vanes, one side is black and the other side is reflective. Yeah, that's true. All right, I'm going to go ahead and shine the light on it. And you guys can see what's happening there.
Yeah. Well, okay, I guess. Can we see what happened?
Well, you can see the thing spin, I guess is what I should
Yeah,
say.
well, see, I guess that was my question. Was it spinning or vibrating? But you said it's spinning.
No.
So.
Well, and it's just slowing down and you can
Yeah.
count it, but it is spinning.
I didn't even see those things in there. I thought that was just like the thing behind it.
Okay, need to see it again?
Yeah.
All right.
If that's the case, then why can't things be light powered?
Solar panels.
They can. Google solar sails.
Or I guess
Solar sails.
I guess solar panels. What am I talking about?
Although solar panels
I got really excited.
don't move solid materials, they move electrical charge, and then use the electrical energy to move things. This is moving an actual
So
solid
the
piece
black
of metal.
side absorbs it all, and so I guess it's pushing it, is that it? And so like the aluminum on the other side just reflects it? I don't know. I
feel
thought it
like
would work the other way around.
It's some sort of like idea about this is a wave of energy. So
Do
it's
protons
slinging
have
into the
mass?
thing, so it has to have some sort of force or mass, and that makes
Or
it go
photons.
on.
it's
And
Wow,
it's
geez.
just you have to have the right material.
Don't
okay,
like
Mr. Bergman earlier
react
was
to
saying
that
photons for a
sensory
second.
integration or whatever.
Okay.
It's
Mr.
all
Bergman,
good.
do photons have mass?
I mean, they're
Well, that's
small,
kind of
but-
what we're after. If